Hi everyone, and welcome to Inverter Always. I'm Dana, and this is the second in a series of videos where we discuss what is VRF. In today's video, we narrow down the conversation as we look closer into mini-splits and the residential VRF heat pump systems and compare how they operate. Now, let's jump right in. Alright you guys, welcome back. Now before we get started today, in the last video we discussed how a heat pump system works and the differences between a traditional heat pump, an inverter mini-split, and a VRF system. If you haven't seen that video yet, I'll put the link at the top. Make sure you check it out. It's going to be really important as today we narrow down that conversation and we really focus on the mini-splits and how the inverter mini-splits work in a residential application. Understanding this is just another step in the direction of getting to that VRF system. We have a lot of content to cover today, you guys. I hope you enjoy the video. If you don't mind hitting the like button below, it really helps out the channel since we're just getting started. So today we have two goals, and the first one is really just understand how your mini-split system works. If you're a homeowner, knowing what that system is doing when it calls for heating or cooling, or if you're a contractor, really understanding the differences between the mini-splits and the VRF logic, the controls, and what they're doing during the heating and cooling cycles. It's super important to understand the differences between these two systems because they're commonly misunderstood as a mini-split can do what a VRF does, and that's just simply not the case. So today my goal for you guys is just really understand, how does your mini-split system operate on a daily, regular basis, and then compare that information with, here's all the things the VRF systems can do that the mini-split systems can't do, or here's what the VRF systems do that's better than the mini-split systems. Because as we discussed in the last video, your traditional heat pump is just bare bones heat pump. The mini-split inverter is that entry-level, high-efficient inverter system. And then when you go to the VRF system, that is really the top of the line when it comes to controls and comfort and efficiency and everything else. So there's definitely some differences between these two systems just in how they operate, and today our goal is to really understand those differences. Now, just as a reminder, there are two kinds of VRF systems. There are single-phase residential VRF heat pump systems and three-phase commercial heat pump and heat recovery systems. For today's video, we're really going to be focusing on the residential single-phase VRF heat pump systems and how they operate compared to the residential mini-split inverter heat pump systems. We're going to be discussing the heat recovery systems at a later date once we've gotten a little further along in the series. Remember, we're still trying to build the building blocks to get to that point. So we're not quite there yet, but we'll be there soon. Now, as we get into the content, let's take a look at the inverter mini-split system. We talked about this as it relates to traditional heat pumps in the last video, but I want to show you guys that there isn't a whole lot changing when you go from a traditional heat pump to an inverter heat pump if you're looking at the refrigerant circuit. This is important because going to a communicating system that has more components is often intimidating and overwhelming for those of us who haven't worked on these systems before. But the goal here is to really just show you it's doing the exact same thing. It just has different components that are more efficient to get the same process done. So if we're looking at the inverter heat pump cycle, just starting with the compressor, when there's a demand for heat, you're going to have a high pressure, high temperature gas coming off that compressor, just like you would on a regular heat pump. It goes through the outdoor unit reversing valve or four-way valve, whichever terminology you prefer. Following this pink line, that's your hot gas line, it goes to the indoor unit, and then as it goes through the indoor unit heat exchanger, the air from your room blows across that heat exchanger and causes that hot gas to reject its heat and condensing into a high temperature, high pressure liquid. That liquid then goes back to the outdoor unit and then through what's called an electronic expansion valve. And we talked about this component in the last video. This is a big difference between traditional heat pumps and inverter heat pumps. When you have a compressor that is adjusting its speed according to the demand in the space, which we'll talk about shortly, you also need an expansion valve that can adjust its position relative to the compressor. So as we discussed, that metering device is what is getting you that pressure drop. So that high pressure, high temperature liquid is then going to become a low pressure, low temperature liquid. That liquid then goes through the outdoor unit heat exchanger and needs to absorb the heat energy from outside. So the goal that this expansion valve has is to get that liquid temperature 10 to 15 degrees colder than the outdoor air. That way when it goes through the outdoor unit heat exchanger, it can pull that heat energy out of the outdoor air. And by the time it leaves that heat exchanger, it should be that light blue line, which is a low pressure, low temperature gas going back to the compressor. This is the same thing a traditional heat pump system does. An inverter system just does it better. So on a traditional heat pump system, you typically have to lock out your heat pump when it gets cold outside, because they just can't efficiently heat your house when it's cold outside. That's why you have backup heat. That's why you have gas furnaces or electric strip heat or baseboard heaters or cadet heaters or fireplaces or something else. When you go to an inverter heat pump, between the compressor, the variable speed fans, and the electronic expansion valve, we now have way more controls and ability to heat at lower outdoor temperatures. And to give you an idea of what that looks like on a traditional heat pump system, you might lock out your heat pump 40 degrees, 45 degrees. If it's a 16C or 2-stage, maybe you go down to 35 degrees, but that's still seldom. With an inverter heat pump system, you can run that year round all the way down to 0 degrees. And on some systems, depending on manufacturer, you can actually go below 0 degrees outside, and the system can still get heat energy out of the outdoor air. It's pretty cool. So looking at the schematic, nothing's really changing. And if you like actual schematics, I went and grabbed one. This one is from Daikin's website, where it shows you the compressors at the bottom left, and in the heat mode, that refrigerant is going to come off the compressor, go through that 4-way valve. It's going to go to the indoor unit. It's going to go through the indoor unit heat exchanger, reject all of that heat energy into the space, condense into a liquid. It's going to go back to the outdoor unit. There's your expansion valve. That's where you're going to get that pressure drop. Then again, that liquid, remember that liquid needs to be colder than the outdoor air so that it can absorb that heat energy and evaporate through the outdoor heat exchanger before it then comes back to the compressor. So depending on which picture is easier to understand, I thought it was important I give you an actual schematic and not just my drawn up one. Now, it's really important to take this, which is definitely more technical for the beginning of the video, but then understanding that from a fundamental standpoint to now, what's the end user going to experience in all of this? Because typically a homeowner is not going to understand what we just talked about. So what I like to do is I like to just take the homeowner through the process. You just got a wall mount unit installed, or a cassette installed, or a ducted unit installed. It doesn't really matter the indoor style. The logic still works very similarly. So if you look at the picture at the top, you're going to be in your living room with a handheld remote controller typically, and that handheld remote controller is like a TV remote. So you point it at your unit and you push a button. If you push the on-off button, it sends that signal to the indoor unit, and the indoor unit turns on. If you change the set point up or down, it sends that signal to the indoor unit, and that indoor unit adjusts its set points. Now, when you do that, you change the set point, the indoor unit is going to have what's called an offset. So if you look at the picture in the bottom left, you'll see that that indoor wall mount is mounted much higher than where we would sit at the couch. And the difference in temperature from where we might sit at the couch to where that indoor unit is physically mounted, you're going to have some stratification. What that means is, hot air, warm air rises, and if we're sensing our room temperature from the indoor unit, which is important to note, you're not sensing temperature from that handheld controller. You're sensing temperature from a return air thermistor which is located at the indoor unit. If you're sensing temperature up by the ceiling, that sensed temperature is typically going to be somewhere around 3 to 3.5 degrees warmer than where you're sitting on the couch. So keep that in mind as we go through the process of how your system is operating. So you give the unit a set point. It has a built-in offset. So let's say, for example, you give the indoor unit a 70-degree set point. The indoor unit is going to say, okay, my target temperature is 73.5. And again, depending on unit, this offset number may vary. On some indoor models, it might only be 2.5. And on some indoor models, it might be 4.5. The typical standard is right around 3.5 degrees. So your target temperature is what the system uses for its control algorithm. And we'll talk about that algorithm in just a second. It's not the actual set point that you give the unit on the handheld remote controller though. You have to remember there's an offset because the unit is mounted up by the ceiling. So I give my unit a set point of 70. It calculates the offset and says, okay, internally I'm going to try and maintain a return air temperature of 73.5. That's that target temperature. So now what happens is something called PID logic. And what the system will do is it will calculate the difference between that target temperature and return air temperature. So if the return air temperature is 65 because it's cold in the house, and you turned it on and you cranked the set point up to 70, it's going to look at that 65-degree return air temperature and try to achieve a target temperature of 73.5. So that difference of 8.5 degrees is what's called the proportional part of the PID logic. Now, the I stands for integral. That's your time-based factor. So how long has that difference of 8.5 degrees been there? Has it been 1 minute? Did you just set it? Has it been an hour? How long has it been? The last part of the calculation is the derivative, which is your rate of change. And so this is where the judgment comes into play that tries to not overshoot that target temperature. So we start out 8.5 degrees apart. The system sees that. It's going to ramp up. It's going to run harder because it needs to recover 8.5 degrees between the target temperature and the room temperature. Now what it's going to do is it's going to monitor how fast it gets closer and closer and closer to that target temperature. And the goal is as it gets closer and closer and closer, that derivative factor tells it to slow down. And the closer it gets to that target temperature, the more the compressor slows down. And the goal at the end of the day is to get as close to that target temperature as possible without overshooting it. So ideally, if the return air temperature can maintain 73, while the target is 73.5, you're within a half a degree, the compressor ramps as far down as it can, the fans ramp down as far as they can, and then your expansion valve closes down as much as it needs to compensate for that refrigerant flow. And if sized properly, and if installed properly, your system should be able to maintain that target temperature relatively easily. There are some caveats though. One of the biggest problems with mini splits is when you have multiple indoor units, because this really starts to change how the unit behaves. So for now, let's just push pause. When we look at a single zone mini split, everything we just talked about is relatively easy. Compressor is looking at one indoor unit and only running that one calculation to make sure that one indoor unit doesn't overshoot the target temperature. But now we introduce another indoor unit. So indoor unit 1 might be in the living room and indoor unit 2 might be in the master bedroom. This is a very common setup or application. I put a unit in my master, I put a unit in my living room, I call it good. Maybe I have a really small house. So when you have 2 indoor units, now you have 2 algorithms. Now you have one compressor trying to achieve two different target temperatures. Indoor unit 1 that's in my living room might be set for 70, which means it has a target temperature of 73.5. Remember, that's the example we just went through that started it with a room temperature of 65. Indoor unit 2 in the master, though, it might have a set point of 72. With the offset built in, that's 75.5 degrees for the target temperature. So now the compressor has to decide how hard to run based on both of those units' PID algorithms. Where you start to run into problems is as unit number 1 starts to get closer and closer and closer to that target temperature. Remember, it has a lower target temperature of 73.5. The compressor is going to start to slow down, but still see the master bedroom with a bigger difference between its return air and target temperatures. So what the compressor can't do is slow down enough for the living room to not slightly overshoot. And so what generally happens is while the master is still calling, the compressor slows down as much as it can to allow the living room to not overshoot, but allow the master suite to still get to that target temperature. But it usually can't slow down enough, and the living room indoor unit 1 will start to slightly overshoot. Now, depending on the size of the units, depending on your conditions, this might only overshoot by 1 degree and you might not even notice the difference. However, it's very common that bedroom indoor units are oversized. It just happens. And so what ends up happening is now you've got a unit inside the bedroom that's calling for more than it really needs. The compressor doesn't ramp down quite enough, and that living room unit then overshoots beyond what's comfortable. And on most brands, again, this is going to change slightly from unit to unit, but on most brands, whatever the offset is the same offset. It's doubled, is a safety to turn the unit off. And what I mean by that is when the unit gets to its target temperature of 73.5 in the living room, it doesn't shut off. The fan goes to low, but it keeps running. Again, this can change depending on model, depending on brand, but the general out-of-the-box functionality of the mini-split systems is it gets to the target temperature and ramps the fan down to low, but it doesn't shut the fan off until it overshoots another 3.5 degrees. Whatever that offset was from the set point is generally the safety offset to shut the indoor unit off completely. So now you're looking at that potential of 7 degrees from the set point. So I might set a unit for 70, have it target 73.5 up at the return, which is up by the ceiling, but then the unit doesn't actually shut the fan off until the return is 77, which means down where I'm sitting it's 74. Well, I wanted a set point of 70. So now I'm 4 degrees too warm. And this does cause comfort complaints. This isn't always a problem, but the more indoor units you add to a mini-split, the higher the risk for these problems are. If I only have 2 indoor units, a lot of the time, honestly, you can be just fine. The goal when you have multiple indoor units is to set them for whatever temperature is comfortable and then leave them there. The last thing that you want is to turn an indoor unit on and create a large delta between your target temperature and return air temperature, which forces that compressor to ramp up. Because then when it ramps up to recover that one zone, all the other zones are going to get all that hot gas as well. You can see in this chart here, when your hot gas comes off the compressor and it goes to your indoor units, out of each port there are no valves preventing that hot gas from going to the indoor units. Every single indoor unit gets hot gas anytime the compressor runs. And so even though indoor unit 1 may not want any more hot gas, it's still getting hot gas. Now, the expansion valve that's on the liquid line side back at the outdoor unit can throttle down and close, but it can't close 100%. It can't stack up the refrigerant all the way back through into the hot gas line. So it has to stay at least a partial way open. But even though it's closed as much as possible, you still have flow. And if you still have flow, you still have heat rejection. So you have to be really careful when you're sizing the indoor units and when you're sizing the outdoor unit, because you don't want the compressor to be too big and overshoot all of your set points. So now let's go ahead and take a look at an actual schematic. Again, just like we talked about before, it's doing the same thing from a refrigeration circuit perspective, except this time we just have multiple ports. So out of your compressor, you're still going to have that hot gas that goes through that four-way valve. Then it's going to go down through basically a header or a manifold, and hot gas is going to come out of all three of your ports. And then what I did here is I just labeled our pretend line sets different colors so you could see where the line sets need to go to indoor unit A, indoor unit B, and indoor unit C. Now, the other thing you have to be really careful about with mini splits, which we'll talk about in another video when we focus on the install, is making sure that indoor unit A, indoor unit B, and indoor unit C all get piped to the correct ports. If you cross these ports, then you're going to have a total disaster. But again, we'll leave that for another day. All these indoor units are getting that hot gas. You can see that there's no valves that's preventing that hot gas from getting to the indoor units. So just be really careful sizing the indoor units, and know that based on what we talked about with the PID control, you're very limited on what that unit can do, especially once we look at what VRF systems are capable of. So as we discussed last time, when you have a VRF heat pump system, we add that second electronic expansion valve at the indoor unit, and it has a ton of advantages. But one of the biggest advantages is your room temperature control, because now when I have multiple indoor units, I can have each indoor unit's expansion valve throttling totally separate directly at the indoor unit, which helps a ton with the refrigerant flow through the heat exchanger. Now, when we start looking at PID control, the VRF systems use a very similar control logic, but by having the expansion valve at the indoor unit, we can add additional PI controls, and that's really focusing on something called superheat and subcooling. And I'm only going to give you guys just a generic overview of this because it gets pretty deep pretty quickly, and we're going to be focusing on this way more with heat recovery systems. But basically in the heat mode, and I don't have this drawn up for heating or cooling, but just verbally to give you an example, that hot gas is going to go to that indoor unit heat exchanger, and what that electronic expansion valve's job is completely to do is control subcooling. So how much heat rejection takes place through that indoor unit heat exchanger, because when the refrigerant leaves that heat exchanger, it's supposed to be a liquid. And then once that refrigerant leaves the electronic expansion valve, it's supposed to have that pressure drop and be a low temperature, low pressure liquid. So how much of that heat transfer takes place can be directly controlled by that electronic expansion valve. And for references, we're always trying to target around 9 to 10 degrees of subcooling. Again, we'll talk about this much more in detail at a later date, but that's something the mini splits can't do. The mini splits can't control superheat and subcooling directly like a VRF system can. Everything has to be done by the inverter compressor when you're looking at a mini split. Everything is controlled off of the discharge pipe temperature. When you go to the VRF system, now I immediately have more components that allow me to directly control the heat transfer at each indoor unit, which by doing this controls the room temperature of each indoor unit much more accurately. Now, to give you an example, when you get to that 2 zone or the 3 zone or 4 zones, VRFs can, depending on brand, have up to 10 indoor units in some cases, all on one heat pump. We're just looking at a very basic layout here. When you go to a VRF system, you no longer have a handheld controller. You are adding a thermostat of some kind, a hardwired remote controller that can sense room temperature at the controller. So we're not using the return air like we do on mini splits. So that 3.5 degree offset goes away. So now if my set point is 70, the unit is going to try to heat or cool to 70. We have additional controls that allow us to have what's called a deadband, a thermo on-off deadband of 1 degree in many cases. Now, this is going to vary slightly from brand to brand, but most of your VRF brands give you the ability to have a 1 degree thermo on-off deadband. And what that means basically is if indoor unit 1 has a 70 degree set point, when that temperature at your thermostat drops to 69, just 1 degree below set point, it's going to call for heat. Now that PID logic is going to kick in, and the compressor is going to see that you only need 1 degree. So it's not going to ramp up. It's going to run very, very low speed. And then it's going to do the same thing for indoor unit 2. Maybe indoor unit 2 wants 71 degrees and the room temperature is 67. There's no offset. It's going to look at that as 4 degrees and it's going to tune to whatever speed it needs to get to. Now, when you have an indoor unit, like in the previous example that we'll use indoor unit 1 in the living room that has met its set point, the fan still doesn't shut off. Just like in the mini splits, the fan will ramp down to the low fan speed to try and prevent any unnecessary overshooting. But with VRF systems, you have the ability to turn off the fan. Now when you turn the fan off, it directly affects the amount of heat rejection because there's no fan blowing air across the heat exchanger. So this is huge. I mean, this is the humongous difference between mini splits and VRF systems, because now I'm controlling the demand within 1 degree of the set point instead of 3 or 3.5 or 4 or 7. With 1 degree, I keep everything running at a much lower speed, and we're doing something called maintaining. And you'll hear me in tons of videos say that the entire point of an inverter system is to maintain the set points. You never want to be recovering, because when you recover, especially with multiple zones, the compressor ramps up and somebody's going to be uncomfortable. Not to mention it's a lot harder for an inverter system to recover than it is to maintain, and consumes way more energy, and their list of problems goes on. So you always want to be maintaining whatever the comfort level is, whatever your set point comfort level is, just leave it there. The nice thing about the VRF though is when that room temperature drops 1 degree, it'll call, and it'll do its best to maintain that set point with no offset. If for any reason it gets 1 degree past the set point, it goes thermo off. It says, hey, I don't want any more heat. Turn the fan off if you want to turn the fan off, or go to low and just ramp down as far as possible. And so now I can have indoor unit 1 have its fan turn off, and now my living room just stays 70 degrees. And indoor unit 2 that still needs to heat a couple more degrees can do so. So I know that's only 2 differences between the expansion valve and then the control logic. It's just scratching the surface. There are so many other things that we can do, like with auto mode. It's a conversation for another day, but the basics is you don't want auto mode on a mini split, and there's a whole list of reasons why. On a VRF system, it's not that big of a deal. You can put it in auto because you're going to be controlling your zones to a much tighter deadband. A quick example, on a VRF system, if unit 1 is in auto, then unit 2 follows whatever mode the system is in, because indoor unit 1 is the one that's in auto. It's the master. If indoor unit 2, it has a set point of 70 degrees and the room temperature is, say, 72 degrees, while the system's in heat, it's thermo off, fans off. It's not going to heat because the room is already warmer than the set point. If indoor unit 1 switches to cooling, well, then indoor unit 2 will go ahead and cool down to 70 degrees and then satisfy again. So it pretty much just always turns the fan off if it's past the set point, so you're never drifting too far from whatever your comfort level is. It's a simple way of putting it. Again, we'll talk about this in more detail at a later date. But when you go to that VRF, and we discussed this last time, some of the biggest advantages are your controls. And we're just scratching the surface. When we get into the heat recovery section, there's a bunch more stuff we can do that's really cool. But from a residential perspective, one of the biggest things we struggle with every single day is comfort. And when we're seeing mini splits time and time again be oversized or undersized and just really lacking the understanding of how does it work, why is it doing what it's doing, and 9 times out of 10 the answer is, well, you should have done a VRF. And the way that I've kind of put everything together over the years is anytime you have 3 zones or more, VRF makes way more sense. And if you have 3 tons of capacity or more, VRF makes total sense. One of the biggest arguments, which we'll talk about at a later date, is cost. The VRF systems cost more, so I'm doing mini splits all the time because they're easier to sell. And I get it, but when you get to 3 indoor units or you get to the 3 tons of capacity, the cost difference is much closer than when it's like 1 zone or 2 zones. So if you have an application where you want 3 or more zones, or your tonnage is 3 tons or more, I really encourage you to look at that VRF as a good solution, because you're going to have all that extra control and an added level of comfort, which means you're going to have less comfort complaints and less callbacks. As a contractor, callbacks are going to eat up all of your margin that you made on the install, and as a homeowner, we just don't want to have the contractor come back and try to fix it later. Let's just have it be done the right way the first time. So to conclude, mini split systems, great entry level product. Super efficient because they use the inverter technology. And when you look at a mini split system, if you have it in 1 zone because you just want to provide supplemental heating or supplemental cooling, maybe to the master bedroom, because the house has a ducted system but it doesn't quite reach the master very well, that's a great option. When you start looking at 2 zones or 3 zones or 4 zones on a mini split, you just need to know up front that you better set all of your set points and then leave them there and don't ever change them, because you have to maintain, otherwise you could very easily have overshooting occur because of the lack of controls the mini split has. When you go to the VRF system, you have the high-end, high-efficient system, and it doesn't matter if it's a single zone or a multi-zone, it has all the controls built in that give you that optimal level of comfort. Now I put 2 things at the bottom as far as the additional controls goes. You're going to find that depending on the brand, mini splits do have other controls options. It's just out of the box, they come with the handheld. And so today we were just talking about how everything is out of the box. You can add thermostats to mini split systems, and we're going to have several videos at a later date that focuses on controls, totally outside of the VRF series that we're in right now. But yes, the answer is you can add more controls to your mini splits to try and compensate for systems overshooting. The one thing I'll tell you though is be careful, because a lot of the thermostats that you add to mini splits will manually turn off the indoor unit as soon as it reaches the set point at the thermostat. It full on turns the unit off. And this is okay in most cases, except a lot of your multi-zone mini splits change which indoor unit is the master when a head is turned off. So you can very easily lose or get confused which unit's controlling the mode of the heat pump system if you have any of them in auto. And usually once you add thermostats, you put them in auto. So you do have to be careful, but out of the box, you're going to have the handhelds and you have very, very minimal control options. On the VRF side, I also put, do you have additional controls options? Because there are more and more and more different controls options coming out that provide more features, but from a functionality standpoint, you don't need them. The thermostats that typically come with a VRF system, you're not getting the handhelds, you're getting an actual hardwired controller, have all of the functionality built in to give you all of the control we talked about today. And again, just remember, brands have differences, so the numbers we talked about today aren't all going to be identical from manufacturer to manufacturer, but a lot of them are very, very close and very, very similar. Now, the last thing I put is pricing is not as different as you think, because when you look at buying a wall mount and a mini split outdoor heat pump, and then you look at a wall mount and a VRF heat pump, the costs are going to be a little bit more for the VRF heat pump. But like we discussed, the more zones you have, the closer they are in price. And of course, this is going to vary depending on where you are in the country, or if you're watching this outside of America, I have no idea what your pricing looks like. But in America, generally speaking, once you get to 3 zones or more, or 3 tons or more, the VRF starts to make way more sense, not just from a controls perspective, but the pricing really starts to get closer and closer and closer to that mini split pricing. So as a consumer, I would look at this and say, okay, I would much rather spend more money up front, even if it's $1,000, to get the top of the line system. I'm already paying a lot more than just a traditional heat pump change out to get that inverter technology. And what's the whole point of this channel? It's to educate everybody, because we want to move forward and push forward towards more sustainable energy, and going with the inverter heat pump technology is definitely headed in the right direction. So as you look at that, and as I look at the pricing and the efficiencies of the equipment, it's absolutely worth it to me to spend a little bit more up front to get that VRF system, because of the controls and because of the added level of comfort that I'm going to have in my home compared to fighting a multi-zone mini split with 4 indoor units. Well, that's it for today, you guys. I hope you enjoyed the video. If you have any questions or ideas for future videos, please leave them in the comments below. I really appreciate your guys' input. If you haven't already, click the like and subscribe buttons below as well. It really helps out the channel since we're just getting started. And make sure you click the notification bell so you don't miss out on any future content. Thank you so much for watching Inverter Always. I hope you have an awesome day.